In this video, I will first define what it means for a derivative to be a rate of change, and then I'll give a few examples of what it means to have an instantaneous rate of change and how that relates to how that is the derivative. So first of all, let's take a look at this function. The graph of, I'll make this f of x. And if I were to take a look at the rate of change, what is the rate of change between this point and this point? Well, it's not gonna be right along that line. It's the slope, the rate of change, that is the change in y over the change in x, the rise over the run between these 2 points. It doesn't lie right on the graph. So that's what we would call the average rate of change between these 2 points. But what if you wanted to know, as you got closer and closer, as this change in x got smaller and smaller? So what about between these 2 points? Well, now it's going to look like we're pretty close to being on the graph. But if you zoomed in, you'd see that it was off just a little bit because this is a curved graph. But still, we have that change in y over change in x. Now I'm going to blow this up and take this spot right here and blow it up here. And now we have this part of the curve drawn. I'll draw it in blue just to stay consistent here. This part of the curve blown up or zoomed in, and we're getting closer and closer to this value of x. Right here, and then right here, and closer. So this change in x is getting smaller and smaller. And that's going to get us to our instantaneous rate of change. It's going to get a line that is just what you would call the slope, instantaneous slope, or the tangent. All ways to think of the derivative. So that change in x, all right, we define this change in x, or we refer to it as a value h. And we get h to be really, really small. Now this part is kind of academic. It's important to understand, and I couldn't even, I wouldn't be able to do this. It would hurt me to do this, to explain this without actually showing this nice little explanation of the limit, and that is the derivative. The derivative, that's f prime, that's the notation for the derivative. The derivative of a function equals the limit as x approaches 0. So that x, that change in x, as we get closer and closer to the real value that we're looking for, it's the limit of the function evaluated at x plus h minus f of x all over divided by h. So this is the change in y over the change in x. Change in y over change in x. The limit of the change in y over change in x, and that's the slope. So the change in y, that's this function, and I should really do it from x plus h, so to the right of x, and this little distance of h, and then this change in y is going to be, what is that distance? What is this value minus this value just below it? I'm drawing it small for a reason, to show that we're getting h smaller and smaller. So what I have there in blue is that change in y. The change in x is that h value. So we have change in y over change in x as h gets very, very small, as x approaches 0. And actually we could go from the left or the right, because h, for that limit to work, we have to approach 0 from the left and the right. But I know the way our brain works, We like to think in positive terms. Okay, so that's the rise over the run, and we're getting that instantaneous rate of change. Now, to give an example of that, let's show a graph, and I'm making this all above the x-axis on purpose. So the whole function, this whole function, I'll call this g of x, is all positive. None of it is negative. But if we were to say, oh, how about right at this point? How about right at this point of the derivative of g of negative 1, 2, 3, 4, 5, negative 5. The derivative, that is the instantaneous rate of change, or the instantaneous slope. Well, that's a tangent, drawn in green there, and that equals some negative number. I'll just try to estimate here. Let's say down 1, 2, 3 to the right 2, pretty close. It's not exactly that, but negative 3/2 is roughly that slope of that green line. Onwards over to here, let's take a look at when x is 1/2. Well, that tangent is, I've purposely put this just off the axis so that you'd have no misunderstandings that the slope is not just 0 just because x is 0, but the slope is at this vertex of this parabola. So g prime, the first derivative of 1/2, that is when x is 1/2, what is the slope of the function? That's what you're really asking there, and the slope there is 0. So any time you have a vertex of a parabola, the slope is going to be 0 at that point. So the derivative of a function at its vertex will be 0. The derivative will be 0. All right, on to another example over here. Here we have, you've already guessed what this is going to be. G prime, that's the first derivative, evaluated at, let's see, x is 1, 2, 3, 4, 5, 6, 7. Evaluated at 7. That equals, what is that slope? It's just about 1, actually. So it's not exactly, but I'll say just about 1. Now, just to make a point here, drive a point home, what about, this is still coming down. This graph was still coming down when x is 1/4. When x is 1/4, we have a very slightly negative slope. When x is 1/4, and the reason I want to give this example is because I want to show the derivative does not always match just the value of the function, so or the value of x. So up here in green, this slope was negative, not because the x value was negative, but because the slope was negative. And in this purple, I'm just going to write the slope when x is 1/4, the slope is a small negative. I'll write that because rather than trying to take a guess, it's maybe negative 0.02 or something like that. All right, this is just a sketch, so we don't know for sure. But the point is that the slope is not the same sign as the x value, nor is it the same sign as the y value. See, the entire graph here is in the positive area. That is, g of x is always positive, or y is always positive here, but we have both negative and positive slopes, or instantaneous rates of change.